Okay, so welcome back to the afternoon session. Today we'll have Emilio Trevisiani and actually Yelleshpur give us an informal discussion on celestial amplitudes and Bootstrap. So please take it away.
Yeah, sorry, I forgot. So thank you very much for this opportunity to talk and for this great conference. So indeed, the title of this discussion session will be Celestial Amplitudes and CFT Bootstrap, and it will be just a very informal discussion. So this is important. So you should ask questions, and the main idea is that I will also pose questions, and also you can try to answer, or we can try to answer them together. And that's it. So I'll start the first half of the discussion. That's the total amount of time will be 1.5 hours maximum, but maybe it's a bit less. And it's going to be shared with Akshay, who already gave a very nice talk, and now he's gonna give his second talk of the day. And so the plan for today is gonna be something very simple. So it's in practice, I'm mostly just start by introducing what is the CFT Bootstrap, but I'll be quick with that, because you are all experts, but it's just to have some formulas written on the blackboard. And then the idea is to look at what are the CFT bootstrap axioms and look at what, like in the celestial CFT, what we have. And just pose questions, just that. And so the second part of the talk will be the one by Akshay will be instead mostly about going beyond MHV and maybe also beyond tree level if there's time. So if you have questions about that, you can also wait a bit, or you can also ask them to me, and Akshay will also be part of the discussion. So I'll start by reviewing quickly what are the CFT bootstrap. What is the CFT bootstrap? So the main idea is that is some axiomatic way to define or solve CFTs. And I want to point out that it's important that for each problem, you may have different axioms, and there are other types of bootstrap. Now it's very famous, the CFT bootstrap, but there are other types of bootstrap in different fields, and so maybe there will be at some point some celestial CFT bootstrap, and so the important thing is that it's axiomatic, and the axioms are very simple. So the first thing is that we start by some correlation function of some local operators, and we ask for them to be covariant, so conformally covariant. And as you well know, this fixes 1, 2, and 3-point functions, and the other higher point function will be also strongly constrained. Another important axiom is the existence of an OPE, which schematically is just the fact that if I have a product of two operators, I want to replace them by a sum over single operators that are weighted by some OPE coefficients. I mean, there's also some dependence here, but I'll skip it for this. And the important thing is that this sum runs over operators in the spectrum of the theory. And these are the OPE coefficients. And of course, if you know this and you apply to any endpoint functions, it means that you can solve any endpoint functions if you know the spectrum and the OPE coefficient. So OK and Cijk is enough to know all the endpoint functions. And the last really important axiom that I want to write is the fact that the OPE should be associative. And when you have this, then you can write that famous well, CFT bootstrap that is just a crossing condition. Primaries. Yeah, you can. Yeah, you can actually just look at primaries. It's much easier. And yes, so here you have a 4-point function. And the idea is just to apply the OPE to different channels and say that this is equal. And so this gives rise to the usual equation where you have C1 to O, C3 for O, and you have this diagrammatic way. To write these functions that arise by doing an OPE, and these are called the conformal blocks. Conformal blocks. And the important thing is that they are completely fixed by symmetry. And so this is the equation that you want to solve, and this is what is typically called the bootstrap equation. So typically in what is being done in the bootstrap community is to add extra conditions, in particular some conditions on the spectrum. And for example, that the spectrum is straight. And unitarity is also very important. And you can also ask for other things like the existence of a stress tensor or extra assumptions. But even just with this kind of assumptions, you can really see that sometimes you really can solve a theory. So you can really compute these numbers to a very accurate precision in a given theory. And okay, so these are the celestial CFT axioms. And now I wanted to go to these were just the CFT axioms, and now I wanted to go to the celestial CFT case. And so here I think it's quite important to notice that even the first axiom, so let's say the correlation functions. So let's say that we want to consider this kind of problem. So we would want to consider a 4-point function, which, okay, as you know, can be also written in terms of a function of the cross ratio. And so this kind of 4-point function, it's already a bit puzzling in the sense that there are actually many definitions that you can take for this. Because so there's for sure the most typical and simplest one would be just the usual Mellin transform, so of all the energies, and so this I can call it a tilde, and this would be a very nice way to define these correlation functions. But it's quite clear, it was very soon realized that if you do it in this way, you always have some delta function appearing, sorry, the opposite direction, that set z equal to z bar. And so it tells you that this Mellin transform, for this Mellin transform, this G is actually a distribution. And so then there were other options to define what you should consider as a 4-point function. And so you have some options with a shadow transform of some operator. Of course, the idea is that if you have a delta function and you integrate it against something, you get a function. And so if you have any kind of integral transform, this will help solving this problem. And so it was used as definition with a shadow or with a light transform, or it's me. Yes, I do, and it's on top of the mic, so maybe this doesn't help. Okay. Good catch. Okay. And so these are some of the possibilities that you can try. And indeed, so these things were tried. I mean, there are a lot of papers now about what is even just a 4-point function that you should consider. There are papers like by Fan, Fotopoulos, Seeberger, Taylor, and Zhu, where you have like a 4-point function when you shadow one of operators. Then there's the group of Brown that tried to like transform some of the operators or all of them, and many other people tried different things. But so one of my questions would be like what should we consider? Like, yes, what? So is there one type of 4-point function, or in general n-point function, that we want that is built out of some transform? Do we want all of them? And if we want some of them, one of the questions is like, why? And what does it mean from the bulk point of view? And maybe since there are already a lot of progresses out there, now we have some partial answers on this, maybe not. Yeah, Andy has.
I don't think we know the answer to this, but I thought the way that we would know the answer, so there's a similar question to this in Liouville theory, right? That took 20 years to solve. And the question would be, we need to find a set. So clearly the operators, if we just take all the Mellin transform operators with arbitrary conformal weights, that's obviously a vastly overcomplete set. And so I think isn't what we need to do is to find some set of operators, just like e to the alpha phi would be vastly overcomplete in Liouville theory. So I thought what we needed to do was to find a set of operators that had the property that they close under the operator product expansion, number one, and number two, their 4-point function, the conformal blocks in the 4-point function contain them and only them.
Yeah, which is similar to the OP if this closed on the OP, yes.
Well, I think it's stronger than that, but well, maybe. I mean, I think we know in the case of say celestial Yang-Mills theory that if we take the conformal weights to be integers, that the operator product expansion closes. But I don't know what the status is of to what extent you can factorize the blocks on that.
Yeah, then Yeah.
It's a
okay.
harder calculation, I think, the conformal block one.
What's the answer to the completeness question? So, for example, for the operators on the principal series, they are complete. But if you now look at integer values,
I think it's extremely unlikely that the integer series, though oddly enough, that is what is the answer in Liouville theory after much work, I think. Though some other things like SL2C, you require another, or like the cigar theory, you require another discrete. It can be a very strange particular answer. But certainly when in the paper that Anna and Walker and Atanasov and I wrote, we scattered on the unitary principal series, but the intermediate states clearly contained integers. So, and Liouville series doesn't close under the operator product, at least not in any simple way, because it shifts the conformal weights by one. So, and then he didn't emphasize this, but they didn't emphasize this, but in the work of Taylor and friends where they shadow, I believe that if you put the external weights on the integers, that the intermediate states are also all on the integers. So the integers looks like the most promising candidate, but I don't know, you know, there are various poles in the integer scattering amplitudes that you have to deal with, that we know some have to be there because of the soft theorems, and yeah, so I don't know what nobody's claimed anything.
You think that with let's say half the integers, or starting with one and then all the negative, you could find a complete basis?
Well, that's possible. That closes under the operator product expansion, but there's also, but in our paper with Anna, the conformal blocks contained the positive integers. It's also possible that just the positive integers are complete. I don't know. I mean,
but sorry, but didn't you have also a light operator? That you would exchange also a light ray operator?
We had also a light ray operator, yeah. And the question is whether, and I'm confused about that. If we hadn't also had the light ray operator, I would, you know, we'd be close to an answer to this question. Taylor did. I'm sorry. I'm sure some of Taylor's collaborators are in the room.
In our case, we can also integrate real part, not just the. So what can you say about this? I mean, in your case, you had, I think, the principal series and also integer.
Yeah, but we didn't know that the stuff in the printable series that couldn't be rewritten in some clever way.
Say it again.
We don't know that couldn't have been rewritten in some clever way.
Right. Plus a principal series. We got actually operators that have real positive dimension. I mean, and of course imaginary part, but all the reals pretty much after a bound.
In real integers.
Yeah. So
that's the Poincaré representation giving that for you. But if I remember correctly, if your external states were also real integers, your internal states were real integers. I can't remember about positive versus negative.
Yes, but we had plus I lambda, so they always had an imaginary part.
Right, you had plus I lambda on your external states.
Yeah.
But if you didn't have plus I lambda on your external states, then you wouldn't have it on your internal states, which suggests that maybe the integers by themselves are a complete basis.
But that means putting all the external states basically to have integer dimensions.
Yeah,
like
yeah.
Make them soft, basically, kind of conformally soft.
Yeah. This is what the twister people do.
Mm-hmm.
Okay. But I don't know if that's the right answer or not. Nobody, I haven't said it. You know, it looks like the most promising thing, I think.
when we did a conformal block expansion of the light ray correlative, we also found that if the external states are integers, you only get integers.
Yeah.
In addition to another light ray exchange, but yeah.
Yeah. So. Yeah. So we don't know.
Sir, I just wanted to ask, how is it that the principal series is forms a complete basis, but then the integers, which are like
Well,
much smaller brackets, that also form a complete basis?
Well, what Pistersky and Shao showed was that the integers are a complete basis for normalizable wave functions. That's not really relevant. That's not relevant for what we're doing. And for example, they're not, they're 1 plus I lambda. And if you just act with them on the Poincare group, you get, with translation, you get 2 plus I lambda. So that doesn't mean, even in ordinary scattering theory, like the Hilbert space of square integral states, if you have a state who's falling off like 1 over square root of omega, 1 over omega, and you act on it with a Hamiltonian, you multiply it by omega, and it's not square integral anymore. So so even the action of the Hamiltonian on square integral states is not square integrable. So powers of the Hamiltonian. So it certainly is a true and important statement. It's just not the same as the question we're asking here, which is for a complete set of states that closes under the operator product expansion.
Yeah. Quick question. So, but these states would be the ones that are plus I lambda. They would be really non-normalizable. Is that correct? I mean, they're not delta function normalizable. Would we ever able to have them as external states in correlators, or just always appear in the intermediate term?
Non-normalizable is a statement about the norm. It's a question of what norm you want to use.
Right.
Of course,
they're not delta function normalizable.
Plane waves are also non-normalizable.
Yeah.
And we've learned how to. They're delta function. Their norm is either 0 or infinity. And in the same sense, the integer states you can define some normalization which is singular like that. But I'm not sure that norm, that Klein-Gordon norm, is not the BPZ norm on the celestial sphere. And so I don't know how important a role we would expect it to play in reorganizing scattering amplitudes as.
So it won't be a problem to get them as external states in correlators, even these states, the ones that are plus I lambda or something like that.
It would be, or it wouldn't be?
It would not be. You don't see it as a problem. That's what I'm trying to understand. Because usually we use external states that are 1 plus I lambda or the conformally soft. So.
Well, many people have been doing that. We've been mostly looking at the integer scattering.
Just to
And
clarify.
certainly the fact that, the W generators and the soft generators are all integers. It's pretty hard to imagine understanding the theory without thinking about integer states, because the symmetry generators are all integers. And so they clearly play some kind of important role in the natural, I would think the natural extension of that. If you have a Gaussian, it's a little bit like if you have a Gaussian wave packet, you can expand it in plane waves, but you can also expand it in polynomials in X. And I think the integer basis is something like, is akin to expanding things in polynomials in X, and the plane wave base. Yeah, the usual thing is like expanding it in plane wave.
Just to clarify, I think we've been talking about either integer or principal series, but you were asking about the neither, which is having any real part, any positive real part, and also an imaginary part. And we're not talking about that. We're either saying that, so this normalizability with respect to the Klein-Gordon norm, or maybe the BPZ norm is for the principal series, but there's a question of what operators appear in the OPE and in the conformal block expansion. And there you're saying that maybe you can just
Well,
get away
I
with
think
that
we
with
don't,
only the
I think we
integers.
don't know. If you take, say, the OPE of two massless, if you assume a coupling between two massless scalars and a massive scalar, Walker, correct me if I'm wrong, you can get, you take the OP of two massless ones, you can get a massive one with any conformal weight. And there's some, it's multiplied by some beta function. Now, you don't want to conclude from that if you scatter two massless scalars, you get, an integral over massive scalars of every conformal weight, right? That's over complete. Only some of those, we only need some of those for a complete basis. And I'm just telling you about things I don't understand, not things I do understand. I'm telling you about things I don't understand, not things about things I do understand. But I think it's an important question. Even the one about the, how do we understand the OPE for two massless into a massive scalar? And this takes on importance because if we want to ask whether massive particles might contribute to soft theorems in CCFT, because energetically massive things have to decouple with energetically soft theorems, but not so for conformally soft things.
Yeah. About this basis, maybe you can also think of that, about the question of principal series versus maybe integers. So with the idea that if you want to Mellin transform back and you have some integral like this, you can pick the poles, and this would give rise from this basis that was on the principal series, give rise maybe to another basis that indeed is just integers. So that may be also another way to say the same thing. So there are two. Is this saying that 45 minutes are gone already? Okay, I was worried. Okay. So yeah, so that you could maybe deform this contour and pick maybe this pulse, and this would tell you that maybe there are two different bases that give rise to the same result. But also about this idea of the spectrum, I think, yeah, I mean, I have all related questions. I mean, they are all related to kind of these problems. Yeah, the other question is about the soft operators, and in general about the spectrum. So we saw that there are some axioms. One of the point of this axiom is understanding what is the spectrum, and of course, on this point of view, it was mostly what was let's say what was the behavior of this function, if it was a distribution of a function or a function. But the other thing that one can see is like some properties of the amplitude that tell you that indeed you should have these integer modes. So you should have these soft operators. And let me just write a table. It will be quick, but just again to have something written down. So you have some soft theorems, and we know that for each soft theorem, and for each power in the energy, you have some operator that is special and that has some integer dimensions. So we know that for example, photons, you can consider the leading, and this will give rise to an operator with delta equal to 1, and okay, depending on the helicity, spin equal to plus or minus 1. And similarly, you can do for the graviton, you can study the leading, which will give you again 1, but spin plus or minus 2, and the subleading gives you 0 and plus minus 2. And then there was always this observation from, now it's a few years ago, that of course this is dimension 0 and spin 2. If you take its shadow, it looks like a stress tensor. So you would write a shadow of the subleading. And this has dimension 2 and spin, well, if you want, minus or plus 2. And this is what the people recognize as the stress tensor and its anti-holomorphic counterpart. And so this is nice, but again, even in this picture, we see that here there's this shadow appearing that is, it looks like important, because if there wasn't any shadow, then you wouldn't have something that is exactly a stress tensor. Now, I would say that, yeah, maybe this picture with this structure of the diamond is maybe, it's a bit helpful, just understanding the fact that when you have an operator with this dimension and this spin, then you would have some, and you have that is conserved as some descendancy relation. So let's say that this, I call it S. So you know that there will be some operator here that you can call T or T bar that is also conserved, and it makes sense that it's kind of that you will have something that looks like a stress tensor. So this, it's good, but still it doesn't tell you if you should consider a stress tensor in the theory, or if it's enough to have the other operator, so it's shadow. So noticing that the global part of, I mean, if you just compute the charges associated to this operator, the global part would be the same. So maybe it's enough to have just this its shadow. So it's not clear to me if we want both operator or just one of them, and if we want both y again. So it seems like here that we had to shadow some operators from the beginning, and here we are taking the soft limit, and if we don't shadow, we don't get a stress tensor. So it's a similar kind of question, but again, it's there. I don't know if you have. It's related to these answers, so you can of course check if there's some set of operators that closes under OPE, and that would tell you something. But I think it's still a bit unclear. And I would add to this a similar picture in higher dimension. So in higher dimension, there are these very nice works by many people, but also Kapitz and Mitra did a lot of work on that. And if you write some similar table, so here it's soft theorems, and here delta J, and you see that for the leading, you would get that the dimension of the operator is 1 and the spin is 1. And so this operator I mean, while here you could recognize this as a conserved current, this operator is just not. So this is something a bit unclear what it is. And while if you consider the shadow of the leading, this has dimension d-1 and spin 1, and this is a nice current. So here it really looks like the shadow is more important than the original operator. And this goes true also for gravity, where you have you consider the leading, and you would have 1 and 2, and here you have d-1 and 2, and this is some sort of generalized current that you can understand through representation theory, and it looks like this kind of generalized current. And so this would be the shadow. And you can go on, and again you find here that you have dimension 0 and spin 2, and this is again a bit unclear what it is. Well, if you take its shadow, then again you find sorry, this is D and spin 2, and this is just the usual stress tensor. So this is kind of pointing out in the direction that the shadows here seem like more important, but it's really unclear to me why. So I also wanted to say that, with Andrea and Yorgo, we are exploring what are these kind of operators. So we are trying to find some kind of diamond structures in higher dimensions. And indeed, they also have some interpretations in terms of representation theory. However, it's not as nice as this current. So even when you can fit them in some nice framework, you still find that the shadow are somewhat more important. So yeah, this it seems like kind of a puzzle to me still. Like, I don't know why we should shadow and what it would correspond to in the bulk. Also, this is a question in general. Like, we have all these transforms, but it would be nice to understand their meaning from a bulk point of view. So I don't know if you have comments on that.
There's a third row, which is the spin 0 row, where you sort of take the soft theorems in the nonlinear sigma model or the sigma model, and that gives you a dimension 0 operator because there's no 1 over omega piece. So that's dimension 0 spin 0, whose shadow is dimension D spin 0, which is also known as a marginal operator. So that's kind of a third case, whereas the shadow transformed is kind of the more natural operator in conformal field theory. And the shadow shows up basically as an integrated marginal deformation that you use to deform the celestial CFT by.
Thanks.
Yeah, there's no constraint on the operator. It's just dimension 0 spin 0.
That's nice. So, well, let's say that this for me is still like some sort of puzzle. Then, of course, there are many things that one can do. For example, one could ask, I mean, this kind of tables, now we know they are like very basic. Then you have all the W1 plus infinity extension. And so also there one can try to see, like in that case, you see that the light transform plays some role. And again, it would be interesting to understand why. And I would also say that in a higher dimension, this extension was not studied. So maybe that's also interesting to see if there is this W infinity in higher dimensions. And also, it's important to say that for light transform, strictly speaking, you should actually use a different signature. So you should go to this 2,2 signature. And so then in this case here, of course, you have more space-time dimensions. And so you can actually decrotate more of them. So it's even unclear if you want to do the d/2 signature, or if you just want to have the like 2 times and d-2. So yeah, there are many options that are open, and these are still there. So yeah, I guess the point that I wanted to make is that there are all these transforms that play an important role, and we can even draw some like table of pros and cons on each one of them. You can see that this is simple, but it has delta functions, and the shadow doesn't have delta functions, but still it's also not quite clear how to define correlation functions, like endpoint functions that are nice and have some of the operator shadow maybe in some sensible way. And the light transform is also nice, but in principle is better in Lorentzian. So that's another question that maybe it's there. Should we actually consider, is the signature important? Should we actually just consider Lorentzian signature? That's another question. I mean, many things seem like to be much nicer in Lorentzian, and where we have light transforms and we have all this W infinity, that is much more natural in Lorentzian. So that's another possible question. Well, I think, I mean, this is the sort of question that I have in mind. If you have any answer or any comment, or otherwise, I think I leave the stage to Akshay. Comment.
Yeah, this is sort of useless comment, but it's really fascinating that these 4-dimensional amplitudes formally look like they should have both an S channel and a T channel representation. That's what you're referring to in the bootstrap. You want to show that the two things are equal. And of course, the hallmark of field theory is that when you compute amplitudes, at least in Feynman diagrams, you sum over S, and then you add the sum over T. So you don't do S or T. And famously, string theory was invented as the supposedly nearly unique theory, or at least the only one they could find like this, in which the sum over S was equal to the sum over T, and you weren't supposed to do both of them. But here we're seeing that there's some way of formulating the expand. There seems to be, at least formally, there's so many details here we don't understand. One has to say this formally many times in every sentence, but it looks like there might be a way in any quantum theory of gravity, which has to have a representation on the celestial sphere, of writing it either as an S channel sum or a T channel sum, not the sum of the two, which is making it sound like we're learning that just the symmetries of quantum gravity are pushing it to be pretty close to string theory. And that, of course, would be extremely nice. But my other comment is, I think that doing the bootstrap would be great, but it doesn't seem like we're very close to that. I think there's simpler problems we have to solve first before we can.
I mean, for me, the bootstrap is just understanding what are the axioms. And so in the end, I mean, like actually applying them, it's a different part, but just
yeah.
understanding
Well,
the
it's-
axioms.
It's a good thing to try to do and see how much trouble you get in with things
Sure.
you don't understand along the way, and then maybe we can clean them all up and do it someday.
Yeah, but yeah, for me it was like even like you want to start and you want to have some correlation functions, and you don't quite know what you want to use for that. But yes, it's true that it's still remarkable that some I mean that this representation could be there, and it was found there in some example. And so even just that, it's really nice. So there's some deep structure that is there, and it's nice. And so that's enough of the motivation. But it would be nice to get more understanding of what is the basic building block for this theory.
It might also be interesting to do. So there seemed to be a lot of progress. It hasn't been finalized yet, but various people with toy examples of celestial holography, and one could look at bootstrapping those.
Yeah.
It seemed like a non-trivial question. Yeah.
Yeah, indeed. Sure.
There are some works in CFT where, I mean, that's been related is the importance of the shadow as a reparametrization mode on the CFT.
Sorry, in the CFT itself?
Yeah, that source the stress tensor essentially. So the reparametrization mode is the soft that source the stress tensor.
Well, I mean,
so that's, I mean, just to reemphasize this shadow thing.
But let's say that in a pure CFT context, you typically don't need the shadow at all. So that's the reason why, if you want, yeah, maybe I should have stressed this, but in a pure CFT context, the shadow is typically I mean, it's mostly used as a trick, sometimes to compute the conformal blocks. And it's just this idea that, yeah, in order to compute a conformal block, you can put like this projector that is basically like, you can write it like this, where this is a shadow operator, and you write this projection where you integrate over this point. And this gives you, in practice, a sum over, this gives you something that you can write as a block plus, very schematically, its shadow. And then there are some ways like to kill this shadow part, and then you compute this block. But this is just a kinematical object, so it's nothing that has to do with the spectrum. So in this program, you never hear about shadows. Like you have you have some operators, and that's the set of operators. There's no shadow there.
I think that's true if you're only discussing an isolated conformal field theory. But I think the point about celestial CFTs is that they actually come in families. So if you had an isolated conformal field theory, but with a marginal deformation, then the shadow transform actually does become very natural, and you do use it in conformal perturbation theory, right? Because if you want to calculate correlation functions infinitesimally close, you insert the shadow of the marginal. And so that's exactly what happens in the spin zero case there. And I think the point is that in these other cases, the spin zero, spin 1 and 2, it's, we're kind of familiar with this fact that there's kind of an infinite dimensional space of vacua in gauge theory and gravity. And what the shadow transform does, it's basically inserting a soft particle in the bulk, which moves you around in that space of vacua. And that's really why it's showing up. So the current is the natural operator in a single instantiation of the conformal field theory. But you have these other natural operators because it's natural to deform that conformal field theory and change the vacuum, either by adding soft photons or by adding soft scale is. And I think that's kind of why they both show up in this example, whereas they don't in normal garden variety CFTs.
Yeah, this sounds.
Indeed, I meant like coupling with matter. So yeah, in the case of coupling matter, the effective action has this kind of reparametrization mode. It's very natural from the CFD, but it's yeah.
If the operator is not soft,
I really only thought about the soft case because that's sort of the only examples I know where you actually have bulk moduli spaces of vacua. There might be some other way to think about the other ones. I'm not sure. But at least for like the leading soft theorems, I think they all have that interpretation, and I'll discuss that actually on Saturday.
Yeah, also when we did this state operator correspondence that Andy was mentioning before, you also saw the natural existence of the shadows, right? Like
Yes.
you needed the unshadowed things to pair with the shadowed operators. So they have a very, I don't know, somewhat physical understanding within CCFT. Whereas I think usually, you know, in regular conformal, I guess, quote unquote, regular conformal field theory, you would define your spectrum of operators without actually using the shadow at all. Here, it seems like you have to actually use the shadow.
Yeah, but in that case, it's because the norm is a delta function, and you want to trade it to something that is a power law, and so you integrate it.
Right. So we're motivated by getting a 2-point function that made sense. But yes, yeah, right.
So
the question is, though, how do you motivate it from the bulk point of view, right?
yeah, but indeed, well, this motivation that, let's say, more like the fact that you have a space of vacua and you're doing something like conformal perturbation theory, that kind of sounds like it's sensible at least. But yeah, I guess that still, even with that motivation, then I'm still, I would still ask the same question. So what is the object that we should compute? What is the correlation function that we want to consider? So should we consider that just the shadow one, or both of them, or?
I think, to me at least, it looks most natural if you are looking at correlation functions at a particular point in the moduli space of the CFT, that you really only need to talk about like the current of natural operators. And when you want to move around in that space, that you would really consider the shadow. Like you're not going to be able to avoid the existence of that operator, because if I have the marginal operator, I can always integrate it and take it in correlation functions and parallel transport around the space. But I don't need to talk about it as you said if I'm only looking at a particular. I think for me the big lesson is just that like the soft particles, they're always shadow transformed, and that means you're doing an integral, which looks like we're inserting integrated deformation into correlation. Basically just about.
And so you would only shadow the soft ones.
That seems the place that it
Right. Other comments or otherwise? Highlight.
No, that's fine.
No, come on.
Thank you. Can you hear me okay? Okay, so there are a couple of questions that I thought of which seemed important. The first of them is, can the W1 plus infinity be extended beyond the MHV sector? And this seems like too hard a question, so I will start with something simpler. I will start with Yang-Mills. And what I will do is I will look at the structure of single soft current, not even double soft. I will look at the structure of single soft currents in Yang-Mills beyond MHV and try to identify some problems with these operators. And after that, I will talk about the infinite order soft theorems derived by Hamada and Xu, and also derived by Li and Lin from gauge invariance, and pose a question as to whether they offer an obstruction in extending the symmetry beyond the MHV sector. So just as a reminder, I call HKS the soft current. This has conformal dimension K, where K is 1, 0, -1, and so on. And S is the spin of the current. And if I compute a correlation function like this, I can try to get some information about the structure of the soft factor just by computing this correlation function and tracking the ZZ bar dependence. But if you recall, the correlation functions are defined as Mellin transforms of the amplitude. In particular, the soft correlator would just be the Mellin transform of the amplitude, where one of the integrals is replaced by a compact contour. But what this amounts to doing is picking out the coefficient of omega to the k in AN in the momentum space amplitude. So rather than going through all this song and dance, I will just look at momentum space amplitudes and look at them in a Laurent series expansion about in omega 1 and look at the coefficients as a function of Z1 and Z1 bar. Now let's see how this works for MHV amplitudes. If I want to compute an MHV amplitude, let's say I want to compute 1 plus, 2 plus, 3 minus, 4 minus, and n plus. This is typically done using BCFW recursion. And the reason there is a simple structure for the soft factor is that using these recursion relations, there's just one term which contributes. There's just one term, and there's only one collinear pole, and the rest is a lower point MHV amplitude. If I actually work this out, the expression that I get is the following. And notice that this is the universal soft factor, and both there are two momenta which are shifted, but the shifts are proportional to the soft particle. And indeed, I can just expand this. If you recall, lambda 2 is just I can just expand this object in a Laurent series in omega 2, and I can also rewrite these shifts in the lambda 2 and lambda tilde 2 as exponentials, and finally I end up with an expression which looks like this. Now it's very easy to read off the coefficient of omega to the k from this, and it's clear because of the exponential here that it's a polynomial. In fact, it's a polynomial of the form C1 plus Z1 C2 plus Z1 bar C3 to the 1 minus k. This is the and this gels with what we expect from representation theory. These are supposed to be polynomials in Z1 bar of a particular power. So far, so good. But the problem, or a theming problem, arises if you try to go beyond the MHV sector, or if you try to go beyond MHV amplitudes. And the problem is the following. Let me focus on a particular amplitude, which is the 6-point amplitude, MHV, with the so-called split helicity amplitude, where 4, 5, 6 have negative helicity, and 1, 2, and 3 have positive helicity. I can use BCFW to construct this again, but now there are two channels, or two BCFW channels which contribute to this. One looks familiar. It looks like a collinear channel, but there's an additional multi-particle channel. And so when you actually work it out and compute the answer,
W1 plus infinity was a soft symmetry of any minimally coupled tree level theory of gravity coupled to any matter. Now, are you asking a different question here, or?
What I'm asking is, there seem to be some issues in what I want to point out here specifically. There seem to be some issues in even defining the soft current when you're looking at NMHV amplitudes. There seems to be some feature of non-locality if you try to look at the correlation function of soft current. It doesn't satisfy the properties that it is a polynomial. Moreover, it seems to depend on where you inserted the soft operator.
So you are questioning our claim?
At least in Yang-Mills.
Well, we were claiming something much more general than.
I haven't looked at the same exercise in gravity amplitude simply because that much harder.
But we claimed a similar statement in Yang-Mills too.
Yeah, that is confusing to me. But maybe if I go through it, you will point out what the loophole is.
Well, we didn't make any claim about loop diagrams.
No, I'm only talking about tree-level diagrams, and I find there is some issue in defining the soft current, the single soft current, and maybe if I tell you the issue, you will tell me where it is wrong. But from what I can see, there seems to be some ambiguity or some non-locality.
Is there a place in our paper where you think something is wrong?
Well, I think looking at the plus OPE, you would there is no way to know whether it's in the MHV sector or beyond the MHV sector. So all the algebra is correct, but I don't know whether it is fair to claim that this extends beyond the MHV sector.
Right. I mean, there's a difference between saying that W infinity, 1 plus infinity, has a natural action on particles of all helicities in a wide range of theories, and saying that you can read off essentially a ward identity for the amplitude when you insert one of these things, right? I don't think you're contradicting anything that's in your papers. Someone correct me if I have the wrong end of the stick here. What claim do you think he's contradicting?
I didn't say I thought he was contradicting a claim. I asked if he was contradicting a claim we made in our paper, and we were careful about exactly what we said in our paper, and I'm hesitant to
I guess
restate it now, but we made a precise claim in there.
Yeah, I guess my confusion would just be, it seems like if you're looking at NMHV amplitudes, defining even the single soft current beyond the sub leading level is ambiguous, and it seems to have some
beyond the sub leading.
Yeah, because the leading and sub leading are fixed by universal theorem. Beyond the sub leading level, and presumably in gravity beyond the sub leading level, these soft factors are not universal. And
but once you have the leading and the sub leading, you have the whole tower, right? Because the commutators of those two give the whole symmetry algebra. There's no extra information. There's no extra constraints on amplitudes beyond the leading and the sub leading. Well, he's talking about gauge theory. Yeah, but gauge theory.
Yeah.
In gravity, you would go to sub leading.
I don't know what's the status of your work with back in 2019. If you work on the sub leading, the algebra was not closing, if I remember correctly. Is that correct? For gravity?
Which one?
I don't know. That was for the 2019 December paper with Monica, and you had completed the algebra of subleading in the gauge sector. Is that correct? And the algebra was not closing, if I remember correctly.
I don't remember that.
I'll check it. I had a question about that question, and also about gravity. The subleading, we know that it is at tree level. We know the soft theorem from gauge theory, from normal scattering amplitudes. What can we say about? Do we know what's the status about this theorem, the subleading in gravity at loops? Do we have some kind of control on that?
Well, I think that loops is, we don't, I mean, the only sort of control we have on loops is, you know, if you don't have the symmetry, then you have more degrees of freedom. So it's the usual situation where it's very hard to have a consistent theory in which, but that's not a.
Okay, yeah.
So we don't know much about quantum, but except for the one result of the self-dual loop corrections where mysteriously everything was preserved. But I thought we did have a lot of control on the classical story or the Wilsonian story, where you have many terms, and certainly Elvang gave this list, which interestingly includes phi f squared for the subleading soft photon, soft gluon, and that's a very interesting thing. I'd like to understand how that deforms the algebra, or if it does. But I mean, if you have a word identity, you can apply it twice, and that's the same as saying that if you have a symmetry, you can commute it and get a new symmetry.
Okay.
But I don't know. I guess you're saying something about some kind of assumption of locality or something that I'm not sure what you're saying exactly.
No, I was asking about the status of the soft theorems for gravity first, because I know the sub-subleading graviton theorem, it's not, we don't know what's the status.
The subleading graviton theorem doesn't get corrected.
Right, but the sub-subleading.
The sub-subleading could, and I think Elving gave a list of operators for those too. She did, yeah. Probably includes phi r squared, right?
Mm-hmm.
Yeah.
But not r cubed, right? R
Not
cubed is too high dimension, probably.
Yeah, my question was about the sub-subleading and gravity, actually. Yeah, that was about loop corrections to that, so.
Yes, loop corrections to that. Well, loop corrections that just correct the effective action.
Mm-hmm.
Loop corrections from integrating out massive fields that just correct the effective action are subsumed in Elvang's analysis. And of course, things we're talking about, Elvang is just the most modern treatment. People were talking about things like this back to Francis Lowe in the 50s for the subleading soft photon theorem. Okay. Yeah. So I guess what's confusing me is the kind of corrections you're talking about, things that are generated by corrections. You're not talking about loop things, right?
No.
So everything's local.
Yeah.
So are you correcting the subleading gluon theorem, or?
No. My question was about gravity mostly, not the other thing that I mentioned. I need to remember also your paper. There was some discussion about, I think maybe I'm wrong. Maybe that was the subleading photon theorem, or not photon, Gates theory theorem. And I think you had computed the commutators between such operators, and you were creating a tower of operators that were completely new. But I need to remember better your paper. That was one of the questions. The question that I asked.
Well, it's very tricky because you have to organize these subleading theorems in the right way.
Okay.
Otherwise, they get very confusing. So Hamada and Shu and Lin and these, they could see that and we even talked about this in our correction about paper about Lowe's subleading soft theorem with Lysov, and it's clear that you get more symmetries by generating these, but if you don't organize it in the right way, you get something messy and uncontrollable, and it actually sort of looks as if you're going to get infinitely many soft theorems that they're just going to keep proliferating, and so it's very nice that you have this just one infinite tower. Moreover, there's just 2 or 3 for case of gravity that you actually have to worry about. That they imply all the rest just by the algebra. So I guess I make lots of mistakes, and there could be a mistake in my paper, but I'm wondering if you're saying there is one, because it sounds like it. sort of.
This I'm not exactly sure what the claim is, but my statement is the following. I look at the 6-point NMHV amplitude, and I take one positive helicity operator soft. The resulting correlation function as a function of Z1 and Z1 bar doesn't look like it has it's a polynomial. That's the first claim. The second claim is that the structure seems to depend on where you insert the soft operator. And in particular, it seems to depend on whether there is a negative helicity operator next to it or not. And the structure of the Z1 Z1 bar dependence seems to vary depending on where you put it. And so that seems like this is different from this is a different structure from what we see from the representation theory. Right, but if I'm just looking at the single soft current, why should I take the collinear pole? It's consistent with the commutator because you're only looking at the collinear pole. Okay. Right.
Wait, so Adam, you're saying there's no inconsistency with what? Okay. Okay, so there is a W1 post-infinity symmetry in its gauge theory cousin in the limited domain of general Wilsonian theories with minimally coupled gravity, minimally coupled Yang-Mills, and probably to be safe, keep out all the elevating operators.
But the soft factors seem to be well defined only in the collinear region, but not you can't read it off from. It seems like you can't read it off from looking at the amplitude.
But that doesn't prevent you from generating symmetry.
I'm claiming that the single soft factor seems to depend on the structure seems to depend on whether it's between two positive helicity gluons or it's between a positive and a negative helicity gluon. But if I'm trying to define something universally as the single soft current of a positive helicity gluon, it doesn't seem to make sense. But it seems, but I don't know how you talk about it without referring to the other insertions. But if you're sticking to the collinear region, I agree. Then there's no problem. But the statement that the single soft current is a polynomial is that seems to be true only in the collinear limit, but not beyond the collinear limit. And yeah, the extra singularities that appear seem to depend on whether the particle is between a negative helicity and a positive helicity or between two positive helicities. Yeah. Yeah, I guess if you're for the W infinity symmetry, I guess the only thing that matters is the collinear limit. So I think for that there's no issue. Yeah. Okay.
So you're concluding there's no contradiction with our claims? Is that right?
Yeah, there's no contradiction with the fact that W infinity extends beyond MHV. But the other aspect that I wanted to,
But that's the question you're asking there.
yeah. The other aspect I wanted to mention were the infinite order soft theorems by Hamada and Xu. I'll be brief, and I will derive this for. I will mention what they are for the soft photons. So essentially, they're derived by starting with an n+1 particle amplitude, and if Q is the momentum of the photon that I want to take soft, I can pull out the polarization vector and still write it this way and write it this way. And of course, we know that this must be true. And you get an infinite number of soft theorems by expanding this to all orders in Q. However, there's a catch here because well, the expansion for this amplitude takes this form. This is the universal Weinberg hole that we know. And after that, this starts at order 1 in Q. And so if you expand the whole thing, the statement Q mu mn plus 1 mu equal to 0 gives you and so there's the whole soft theorem is not given just in terms of lower point amplitudes, but there's an extra piece which is not universal. And the best you can do is contract it with, and you can show that the only part that survives here is antisymmetric in all the indices nu1 to nu-l. And so the best theorem that you can get is by contracting this with a symmetric symmetric tensor, and then the statement just becomes yeah. You can show that you can in general decompose it into a symmetric traceless plus trace plus antisymmetric, but you can show that the trace drops out anyway. And the symmetric has to be 0 by itself. Okay. So the only thing that survives is the antisymmetric part.
Thanks.
Can you remind me, they showed this for any, they showed this in gauge theory and in gravity for tree level, or?
This is a, this is a non-perturbative statement. This is valid as, well, the way I've written it, this is the soft photon theorem. And it's valid. If I want the soft gluon theorem, then I just drop the sum because I'm looking at color ordered amplitudes. But in principle, this is valid non-perturbatively, because this is just derived from a word identity. I guess another question is, this seems to be a statement about some part of the amplitude, and the extra piece n that occurs here vanishes in MHV amplitudes because I showed there this factorization is exact. So I guess another confusing aspect is why this does not matter when does it not matter that there's an extra piece, or does it not matter that the statement is about an amplitude or a projection of the amplitude?
Number of soft theorems is only for MHV.
No, this is the infinite number of soft theorems, but it's for a projected piece of the amplitude. It's not for the full amplitude. But if you're in MHV, in the MHV sector, then it is for the full amplitude because this just vanishes.
Okay. So for the full amplitude, it's only the MHV sector.
Yeah. So it seems like these soft theorems govern the projected piece of the amplitude. Is this a contradiction, or is this also consistent with the fact that we have an infinite number of soft theorems from W infinity? And I mean, I haven't shown it here, but they also derived a similar set of identities for gravity. This is not something I understand, but on the face of it, it seems puzzling that these are only able to govern a piece of the amplitude as opposed to the full amplitude.
What's the status of putting, like, classifying what kind of ends you have in what kind of theories? Like, what kind is non-universal PSP?
Oh,
you fix the theory, then you have some.
In this paper, they work out some examples, I think, in QED maybe, but there's no work, I think.
But do you know what's the general status and what kind of?
I'm not sure, but I think they mentioned that they're non-universal, and it's not clear how one would proceed to. The paper I've got this from is the paper by Li, Lin, and Zhang, who essentially rederive the statement by Hamada and Xu using gauge invariant.
Hello. Hi. Yeah, so the currents that we derived, the W1 plus infinity currents, there's an argument in CCFT where you show that like the contour integral around the soft operator can be transformed into a contour of infinity plus the contributions from the other insertions. And so for the leading and subleading in gauge theory, there's no contribution from infinity. And you can show this just by the weight of the current.
Yeah.
But beyond, so for leading and subleading in gravity and only leading in gauge theory, this is true. And then beyond that order, there's going to be contributions from infinity. And those would correspond to these non-universal terms in the soft theorems. And I'll talk more about this tomorrow too.
Okay.
Yeah. I mean, I guess they're soft insertions at infinity, but they're part of the I guess, yeah, but they're not as it's usually. Yeah, they're part of the theorem. Yeah. And so this universal term is only talking about a part. The universal term in this like infinite set of soft theorems is only looking at a part of the amplitude, the one that's like singular in 1 over q dot p. And the rest of the terms are not universal and they're not constrained.
Right. So, but I guess my question is it then fair to say that this is a symmetry of the amplitude, or is it a symmetry of a projection of the amplitude in general?
I mean, I think it's it's not a symmetry insofar as you can, take a contour around all the things in the bulk and say they're zero, but you can if you include the stuff from infinity also. Yeah, exactly. Yeah. Yeah, right, exactly. So it depends how you want to say it, but it's the soft theorem. Yeah, yeah. Yeah, yeah. Right, I agree. Sorry, maybe I'm confused. I think we're on the same page. Yeah. No, I mean, this is also the soft theorem, right?
Yeah,
like
these are in the limit q going to 0.
There's just extra, it includes the extra terms.
They're only after you project out a piece of the amplitude.
No, the whole amplitude, including the extra terms, is the soft theorem. You can do something to project those things out.
Yeah.
Yeah. I think we're all on the same page, but maybe not.
Well, you and I are on the same page.
I guess the tension is, but you can make a statement that some projected piece of the amplitude satisfies this soft theorem, but is it then fair to say that it's a statement about the full amplitude?
I think this is the same question as if you ignored the thing if you just, you shouldn't do this, but if you just ignore the thing at infinity, you'll find a conservation law for the points in the bulk, but you have to include that contribution at infinity. And I think that's just what this is doing, probably. No, the extra term is the extra contribution at infinity, and the subtraction is taking it out. So you can say we can only look at this collection. So. Right. I mean, there's a conservation law between soft and the hard charges. Yeah. But there's no global conserved symmetry. Yeah.
Yeah. Right, it's an exact equation. There's no dropping of it, yeah. That's all I had to say.